Hi friends, I'm so excited. Today I'm going to talk to Dr. Jack Hewitt, and what we're going to do is we're going to discuss gamma burst radiation, detecting it out in space, what that means for us. So, with that guys, let's get going. So what got you initially into astrophysics and what made you want to go down this route?
I think so. The thing that got me into astronomy and astrophysics was at Northwestern, where I went to undergrad. I remember being on the campus tour, and we were kind of like going around. It was kind of boring. But then right next to the big tech building, there's this tiny observatory from the 1880s that they built. And I was just like, this is a really cool building. I want to check this out. And that seeing like this old like kind of piece of history, and it kind of made me, I was like, I'm kind of interested in astronomy. I was going to go like into physics. I was always interested in black holes and particle physics. I remember one of my classmates in 5th grade, he had a brother that was going to MIT, and so like he was like, I have the smartest brother ever. And he sent me this book, A Brief History of Time. Mm-hmm. And so he let me borrow it, and I never gave it back to him because I kept it and I didn't understand it, but it had some like cool sketches and pictures in it that I was trying to understand in 5th grade. And so that's at Northwestern. There is a professor working on the center of our galaxy, which is the closest supermassive black hole. And at the time, it was like the closest confirmed black hole that we knew about. And so I wanted to work with him, and that got me into radio astronomy and like other things. One thing leads to something else that's like, there's opportunities in different places, so you just kind of follow this random walk through science. NASA Goddard Space Flight Center, which got me into like gamma rays and Fermi, which is where I've more or less been since my postdoc. Now I'm working on using like gamma rays to understand what accelerates cosmic rays in our galaxy, and it does tend to be things that are very energetic. So those are always interesting, like stars exploding or black holes and neutron stars, like really dense compact objects.
Okay.
So I don't know, it's always fascinated me. I didn't really get to become a theoretical physicist that works on black holes like Stephen Hawking, and that's fine. I don't think I was ideally suited for that anyway. But that interest has like kind of propagated through. I'm still like interested in those things and still in a way studying related things.
Okay, so could you explain to me exactly what a gamma burst is from all these high energy activities?
All right, so gamma rays are the highest energy of light. So whenever you have something super energetic, like matter under the extreme gravity near a black hole, or like an entire star imploding and exploding, you get really high energy light. And so often these sources are really bright in X-rays, which is just a step down from gamma rays. And gamma rays, though, are like this huge part of the electromagnetic spectrum. It's basically like everything above X-rays is a gamma ray. So it's like orders of magnitude. It's as many orders of magnitude in gamma rays as there are in almost the rest of the electromagnetic spectrum down to radio. The first gamma ray sources were discovered by the military.
Really? Okay.
When they were looking to basically see our other countries, Russia at the time, testing nuclear weapons above ground where we could see like bursts of gamma rays.
Right, okay.
And so they discovered that there were bursts of gamma rays coming from basically all over space. Okay. And they didn't tell anyone. For years, they didn't tell anyone.
Of course not.
And then eventually, like the astronomers figured it out as well. They built gamma ray detectors in space. Actually, they put them on rockets at first and launched them into space because you really can't see gamma rays from the ground. Fortunately, like the Earth's atmosphere absorbs all these gamma rays, and so we have to basically go to space to see them, or now for the highest energy gamma rays, they build telescopes on the ground that see nanosecond flashes of UV light caused as like a single gamma ray tears through the atmosphere.
Wow. And
when it does, it'll maybe interact with some like electron or oxygen molecule or nitrogen molecule, and there's so much energy in that one piece of light that it just causes a shower of other particles to be created, and this literally like rains down through the atmosphere in a billionth of a second or a few billionths of a second.
Right.
And so you would never see this, but now with semiconductors, they have cameras that are fast enough and sensitive enough in the UV that you can see these showers of particles coming down, and it creates like lower energy light that a large telescope can detect. And so what they did is they built these really large, like 10-meter optical telescopes, which you would never use to look at stars, because the way that the telescope is designed, you never get like a nice pinpoint star, but you collect a lot of light.
Okay.
And so you can see these like instantaneous flashes. So it's really neat. And they're building this giant array of these telescopes in South Africa right now. And so this is going to be like the next big thing in astronomy, in gamma ray astronomy, which is called the Cherenkov Telescope Array. And so they're like really excited about all the cool things they're going to be discovering. Meanwhile, there's really not that many gamma ray telescopes that are working.
Right.
The one that I work on, Fermi, has been around 15 years now. I joined the project like right after launch, and so when I got there, they had their first results and like all this exciting stuff, and it was a great time. And now, like 15 years later, you kind of look back and you're like, oh, it's like, yeah, there's a lot of discoveries that have been made, and some of the initial discoveries, it's time to kind of go back and revisit those discoveries.
Right.
There's so much more data now. But in the meantime, they found all these other sources they weren't expecting. And in the last year, like you're talking about gamma ray bursts, they found, what they say, it's like a 1 in a millennia gamma ray burst.
Really?
It was by far the brightest gamma ray burst that had ever been seen. And so I forget how long it was, but it was a short burst that just peaks in gamma rays. But then you can see this, it's essentially a star exploding. Well, exploding, but the core of the star is collapsing and actually has enough mass where it just directly collapses into a black hole. And when that happens, you go from having, like, if you think of the core of a star, it's much larger than the Earth. If you collapse that down into something that's basically the density of an atom, you get a neutron star. So that's something the mass of the sun, the size of like Duval County, right?
Yeah.
The size of a city. And at that point, like, you have such extreme forces, but if you collapse it even more, now you just create a black hole. There's nothing else that we know of beyond a neutron star. And you get to just extreme gravitational forces. And so this neutron star, like all the material, the black hole in the gamma ray burst, all the material around it is probably like being crashing down. And some of it eventually forms like an accretion disk that's falling onto the black hole that produces jets that are streaming out at very, very, very close to the speed of light. Like, you cannot accelerate matter to the speed of light, but you can get really close. And this is about as close as you can get. And so these jets of material that are just flung out from the star, there's probably like all these collisions and shocks within it, and that like creates even more higher energy particles, and it just produces this like flash of gamma rays that we see. And it all happens within like seconds, right? So so this was fantastic. It's not something that I've really studied a lot, but the people that I work with, I remember they were like doctors in grad school, because they would get a notification on their phone that like there had been a gamma ray burst, and they're like, oh, gotta go to work. Something just happened. We have to point like every telescope at it to see what we can see. And they would have robotic telescopes all over the world, because you never know where this is going to happen. And they would try to point like other large telescopes like in space, like Chandra is an X-ray telescope, or Hubble, an optical, and that tells them a lot about how massive this star was and what process created the gamma rays, because we still don't really understand how they work, right? In detail, we don't know. We know the big picture, but like the devil is in the details.
Right, of course.
And yeah, there's all these really, really high energy particles flying around space called cosmic rays. And the highest energy cosmic rays we still don't know the source of. Gamma ray bursts are one of the best ideas we have, because there's so much energy released in this formation of this like stellar mass black hole. And those cosmic rays, which we can now see, like some of them do reach us on Earth. A single like proton has the energy of like me throwing a baseball. So this is an incredibly energetic particle. Yeah, it's amazing. And this just crashes through the atmosphere, and it can be seen through its shower of particles. And yeah, so this gamma ray burst that just happened, the particles from it maybe will someday reach us. We'll have no way of knowing. This was in a different galaxy, but it was like a relatively close galaxy as gamma ray bursts go. These things don't happen too much. They probably happened in our galaxy before, but the time scale for one to happen is probably 1 million years or so. So we're probably not going to be alive when we see one.
When we see another one.
Yeah.
Wow.
So this was really, really exciting, and they're still studying like all the data they got from this just being so nearby. They could see like fainter optical emission that they couldn't usually see. So there's lots of data there to work with and model and try to explain. Yeah.
I'm blown away. I'm having a hard time remember any other questions because I'm just fascinated by how this happens. So it collapses in and releases just high energy, of course, right? And you said the cosmic rays, and so what's the difference between the cosmic rays and the gamma rays?
So cosmic rays are actual particles.
Okay.
So like they have mass, they're protons or maybe some iron, heavier nuclei like iron. And the gamma rays are just pure energy, right? Electromagnetic fields propagating through space. And they have enough energy that they can actually, like if they interact, they can create other particles through nuclear interactions. But, the energy scales that we see, like we cannot get these with our, multi-billion-dollar particle accelerators. You can only see it when nature makes it right now. And so, the energy scales are like, let's see, be roughly 1 million times higher than anything we can do with the LHC, right? The best particle collider we've ever built. So it's
and still that's just baby energy compared to what you're able to see.
Yeah, that's not like really high energies, right? It may be high enough to see like the Higgs boson and discover new things about particle physics, but it's not that high for astronomy, right? Of course, we have no control over what happens in space. So the fact that they saw this like maybe 1 in 1,000 year event was really like fantastic.
No, that's amazing. Yeah. So a once in a lifetime, you guys just happened to build it right in the time scale of observing these things. Just built it, bam.
I mean, it was either it's incredibly fortunate or we totally underestimated how often these gamma ray bursts happen. I mean, right now it's probably a little bit of both. But